Hey everyone, let's look at the three ways that you can calculate torque. And the simplest method to understand is just straight up using the formula, which is gamma equals RF times sine theta. And I find using this formula really is easier if you think about the R and the F as vectors. So if there's a door over here, and here are the hinges, and imagine we're above the door looking down at it. Someone comes along and exerts a force on the door like this. That force is being applied at this point. To use this formula, I find it easy to imagine, instead of it pushing the door, think about that force pulling the door so that the tail is being applied to the object. If you do that, then you can draw a position vector from, let's see, this is the axis of rotation over here. The position vector would be from the axis of rotation to the point of application. So that's a vector. It locates where the force is on the object. The force is obviously a vector, and there's always going to be an angle that you can measure when you arrange these vectors like this. That angle's right here, theta. So really this formula uses the magnitude of R, the magnitude of F, times the sine of the angle between them, because in reality this formula is called the vector cross product. That's the definition of the vector cross product, but IB doesn't care if you know that. And they don't care if you write the formula with magnitude like that. But, so the simplest way to understand calculating torque is just straight up use the formula. Find the magnitude of R, find the magnitude of F, find theta, plug everything in. It gives you a number. We'll call that method 1. By the way, the units of torque you can get from looking at the formula. So R has units of meters, and F has units of newtons. Sine theta is unitless, so what are the units of torque? The confusing thing here is that the units of torque are Newton meters. We've encountered that before. And the place that we encountered it before was a Newton meter is a joule. The difference here is hidden in the vector tools that you use to calculate these things. And often when you just use this formula, that vector nature of this is hidden from you, because for work, when you calculate work, you calculate force times displacement times the cosine of the angle between them. This is actually a dot product between vectors, and it results in a scalar quantity, which is newtons times meters, which is joules. So energy is a scalar, doesn't have direction. Newtons times meters calculated in this manner is joules. For torque, we are actually calculating a cross product, and the result is itself a vector, and the units of meters times newtons have a different relationship to each other than they do when you calculate work. Over here, the force and the displacement are in the same direction, or lie on the same line. That's what the cosine theta does for you. It takes a force that might not line up with a displacement, and it calculates the projection of that force on that vector. So they lie in the same line. And so it's meters times newtons that are lined up. When you calculate torque, by the nature of the cross product, you are taking one vector and multiplying it by another vector, and you get a third vector as the answer, which is perpendicular to both of those other two vectors. So this is R and that's F. This is what you would get. Now again, IB does not care if you know anything about cross products or dot products. You can ignore this diagram, but it is confusing that newtons times meters are the units of torque, but they do not equal joules. But important. Confusing but important. Okay, method 2 for calculating torque is very convenient sometimes, but equivalent to method 1. Well, all three methods are equivalent, otherwise you couldn't use them all. So imagine we have a rigid body that has an axis of rotation at point A. So that means the rigid body is rotating around point A. And now let's say force is applied over here in this direction. And that force exerts a torque on this rigid body. And if we calculate that torque relative to point A, we could use method 1, which would mean drawing a position vector from A to the point of application of the force, and then proceed as normal. We could do that. But then obviously I wouldn't have called this method 2. So instead what we're going to do is look at the force and find a line that force lies on. That line is called the line of action for that force. Then find the shortest distance between the axis of rotation and the line of action of that force. So that distance will be called R perpendicular, because it's always going to be a line that's perpendicular to the line of action, and that goes through the axis of rotation. So the way that you calculate torque then would be R perpendicular times F. That's it. And somehow I lost the rigid body. Okay, there it is. It will often be clear in a problem what this distance is, and it might be faster to use this method compared to method 1. And we will prove that this method is equivalent to RF sine theta. In a homework. It's just some right triangles, really. But if they weren't equivalent, then we couldn't use it. Okay. Method 3. Method 3 is similar to method 2. We've got a rigid body. There is some axis of rotation. and there is a force exerted on that body that exerts a torque around point A. Instead of using the perpendicular distance from A to the line of action and calculating R perpendicular times F, note, instead of doing that, we're going to use the perpendicular part of F to the normal R position vector. So here's the normal R position vector just from the axis of rotation to where the force is being exerted. And we're going to multiply the perpendicular part of the force. This also, depending on the context of the problem, might be faster than the other two methods because you might be able to just see what that is. In this problem, it looks like this force can be resolved into two components. And the components that are relevant are the components that line up with R and the component that's perpendicular to R. So this one over here would be F perpendicular. If you look at this one, this component of F lies in the same direction as R. So theta for this one will be 0. So you can think about this part of the force not exerting any torque around point A. This would be like me pushing directly out at the end of the door, lining up with the door. You know, it doesn't exert a torque. So you're focusing on the only part of F that actually exerts any torque around part A, and that's the perpendicular part. And so it's kind of easier to see why in this one it's equivalent to method 1, because if this is theta, I could get the same, the sine of these two angles, theta 1, theta 2, is the same thing, because the sine of supplementary angles is the same. So F perpendicular over here is F times sine theta 2. So if I replace F perpendicular right here with F sine theta, it's easy to see how this is equivalent to method 1. But if you're using this method, you really don't even need to think about angles. You just pick the part of the force that's perpendicular to the position vector. And that's it.